Okay, so from our previous meeting, we already talked about precipitation. Last meeting we finished in wait, I'll go back for previous slides. Wrong click. So from our previous meeting, we talked about precipitation, which is about the rainfall data presentation. So it can be presented in the graph form or in the diagram form and table form. And now in today's class, we will also talk about the rainfall data, but it is mostly regarding the calculation. So as we know from our previous meeting, we haven't talked about the calculation yet. It's only the data presentation and how to acquire the data, how to show the data to the audience or etc. And today we will talk about how to calculate data, and there will also be exercise. As far as I know, usually there will be exercise regarding the average data rainfall calculation. It is similar with the exercise from our previous meetings. It will be done in the same time with the other class. So I think it will be on the next 2 meetings or so. I think there will be exercise next week or next 2 weeks. I haven't sure about that because it will be done with other class also. So we will see. And now, before the calculation begin, we have to have the complete data of the rainfall. What happens if we have the rainfall data which is not complete, rainfall data which is incomplete, or there is loss of rainfall data? To complete them, there are several methods. Here, the mentioned methods are average method, normal ratio method, graph correlation method, and inverse square distance method. We will talk about those methods today. And after that, we will also talk about the how to calculate the average rainfall data. Here, we have the first method, average method. If we have an incomplete rainfall data, we can use this method if the average rainfall for which data is incomplete has less than 10% differences with the station's annual average rainfall index. The average rainfall index here is the station with complete data. As you know from our previous meetings, we all already know that we can get the rainfall data by using the rain gauge in rainfall station. In one rainfall station, the data can be different with the other rainfall station. But if the rainfall station located near, for example, here in the picture, we have 5 rainfall stations. namely A, B, C inside the watershed, and there are 2 rainfall stations outside the watershed here, rainfall station C and E. If you want to calculate the rainfall in this watershed, it is better if you use the rainfall data from all the stations. Here we have 5 stations. It is also okay if you only want to use the 3 data from the station inside the watershed. It is only okay, but the more station that we use, the more accurate the calculation that we will get. In this case, for example, the station D data is incomplete. Here we have station D. What does it mean with incomplete data? For example, data for example, in 1 year, there are daily rainfall data. As you know, 1 year consists of 365 days, and you should have like 365 data of daily rainfall. But in this case, for example, in station D, there's only like 364 rainfall data, but in other station, the rainfall data is complete for 1 year. There are 365 data. So how do we get the lost data? We can calculate it by using the data from other stations. Here in average method, we calculate the average of the data. For example, here we only use the station BCE because location-wise, the BCE is nearer to the station B than station A, because station A is quite far from station D. And the minimum data used is 3 stations. So it is okay if you only use the BCE data, but it is also okay if you want to use the BCEA data. So if you only use 3 data, you can calculate the average by divided with the number of the data. In this case, it's 3. Or if you use the station A also, you can calculate with the average data by dividing it with 4, because you use data from 4 stations. This average method can be used if the average rainfall for this station has less than 10% differences with the other stations. How about if the station with the lost data has more than 10% differences with the other stations? You can use other method. Here we have normal ratio method. This one can be used if the differences between the annual average rainfall for which data incomplete has more than 10% from the station with the complete rainfall data. Same as before, you can also use the 3 data from 3 other stations, or you can also use the data from the 4 other stations. It's both are okay, but it can make the divided. This one is divided by 3, but this one is divided by 4. So it depends on how many data that you use. There is also one variable here, which is not used in the previous equation. For the average one, we can only use the rainfall data, which is R. Here we have rainfall from station B, C, and E. But in this normal ratio method, we have the average annual rainfall, which is symbolized by N here. And here means the average annual rainfall in the place where data is missing, which is in station D. But there is also an A and B and C and E. And there should be no B, no D here because D is the missing one. This is the mean annual rainfall at station index. The mean annual rainfall or the average annual rainfall is the same, right? It's the average value of the rainfall in each station. There's also other method. This one is not related to the differences between the complete or incomplete data. This one is graph correlation method. This is only used if you want to find the missing data by the annual rainfall. So from the previous one, we can look for the daily average data or the monthly data of the rainfall. But here for the graph correlation method, it is only used if you want to find the annual rainfall. For example, from 10 years, there are data of the rainfall in 2010 until 2020. But there is lost rainfall data in, for example, 2015. So we can look for the data for 2015 by using this graph correlation method. And we use this method by describing the correlation of rainfall from the rain station whose data is missing with the index station. The index station means the station with the complete data. If there is a relationship between the two data, then the missing data can be estimated. If there is no relationship, it is difficult to predict. Here is example between the graph correlation method. If there is correlation, usually we can like make the line from the data. But if there's no correlation here, we see the graph on the left. There's no correlation, like the data is not really related. So we cannot use this graph correlation method. And the last one is the inverse square distance method. It is related to the distance between station for which data is missing to the station index and which data is complete. So here we have station D with the missing data, and here we have the distance between station D to station A. This is between station D to station B, and this one is the distance between station D to station C, and this one is the distance between station D to station E. So it depends on the distance, and the distance is because of the name of the method, inverse square distance. So the distance is inverse and then squared and multiplied by the rainfall of each station with the complete data. Yeah. And how do we check the rainfall data? Is it correct or not? Or what if there's changes in the rainfall data? Which one is the right data, or which one is the not accurate data? Here, for example, if the station is moving, or if there is changing in equipment of the rain gauge in each station, there will be also changes in the recorded data. For example, we have in one station, we have a rain gauge which is already old, so it's not accurate anymore. And then they decided to change it. And after they change it, the data become more accurate or better, and then the recorded data become different than the previous data. The data is not so like here we have the line. For example, in year 1978, they changed the equipment, and from here we have the rainfall data from year 1972 until 1977. And then after 1977, there's changing in the equipment. So the line drawn is different. As you can see here, at first the line is in this slope, but after they changing the equipment, or they move the station, or they move the rain gauge, for example, the line become like here. Like in 1978, they're changing, and then 1979, following the 1978 line, become like this. So the change in slope of the correlation line indicates a change. For example, in changing in the station, or changing in the equipment, or in the rain gauge. So we can check this data if there is changes or not. How can we check? From the curve, it can be seen that in 1978, there was a change in the correlation line. Here we have this line and this line. Each line has different slope. Or here we use I as slope, and there is I0 and Ix. If the meteorology changes, the index station will also change, so that the correlation line doesn't change. With the change, the data before 1978 must be adjusted to the data after 1978. So this data right here, the old data, has to be adjusted to follow the new data, because from these changes, it can be assumed that the new data is better than the old data, because it's maybe has better equipment, or maybe has better rain gauge or rainfall station location. So we can adjust it with this equation. Here, Rx is the rainfall data that we are looking for. We're gonna get after we adjust it. The R0 is the rainfall data that you want to adjust. It's the old data, and multiply with I0. I0 is the slope of this curve from before 1978 data. So this old curve, and then the Ix is the slope of the new curve. Then after that, we can adjust it, the old data, to become related to the new data. So the line is not bending like this, so it will be like a more continuous line. And after we got the complete data, and after we got the right data with the changes, and we already adjusted, we can also calculate the average rainfall of a watershed. So as you know, we got the rainfall data from rainfall station. The data that we got is the point rainfall. So from each station, we got each point. From each point, we got data. And it means we got the rainfall data from each point, and then it's called point rainfall. And then after that, we can also calculate the rainfall area by using those points. So in one area, usually there are more than one points, means more than one stations. And after that, we can calculate the rainfall area based on the point rainfall. And there are several ways to calculate the average rainfall. For example, here, we will not talk about all of the methods, because usually there are these four. The top four is the methods that are usually used, and the arithmetic method, arithmetic mean method, and the Thiessen method is the most simplest and frequently used one. So we will talk more about these two, and isoyet we will talk about it a little bit, and intersection line, I think we will also talk about it a little bit of it. And there are also depth elevation method, mean areal elevation method, and hypsometric method. For this depth elevation and mean areal elevation is rather more complicated, because the data that are needed is not only point rainfall, but also the elevation of each area. So it's more complicated, so it's rarely used. Usually the method that frequently used are this arithmetic method, Thiessen method, isoyet, and intersection line method. The first method is the arithmetic mean method. It is also similar with the previous method, the average one, but this one is rather different name. But actually it is also used by using the average equation. So here we have data point rainfall at station A, B, C, D, E. From previous problems, we got station D, which incomplete data. But here, if we want to calculate the average rainfall in an area, we have to get the complete data first. So we already got the complete data, so we can calculate the average of the rainfall data in one area. Here we have data point rainfall at station A, B, C, D, E. And then we can calculate the arithmetic mean method with this equation, because here we have 5 stations. We have to calculate it by dividing it with 5. And after that, we got the average rainfall. So this arithmetic mean method is so simple, but it's not that accurate. So I think there will be constraints in using this equation. For example, if you have an area with different distance between the station. For example, not like in this picture. In this picture, we can see that all of the stations has similar distance with each other, right? It's not that far, it's not that near, but similar. It's not the case if we have, like here, we have, for example, station E is located far from the watershed. So if that's the case, we cannot calculate it with 5 stations, because it will be too far from the watershed to the located station. So the amount of the rainfall which is recorded in the station will not represent this watershed correctly. That's one concern. And other concern, if you have area with different contour, for example, here in one watershed, For example, here in one watershed, we got mountainous area in the area of E. In station E is located in the mountain, but station A, B, D is located in the valley. So it's down, and this one is the upper side. If that's the case, you cannot also use this E station because the rainfall recorded in the E station will not represent the watershed good enough. So that's why if you use the arithmetic mean method, you have to look for your watershed situation. If it is in the normal area, like all of the stations located near and then located in the same elevation, there's no not only one station located in the mountain, the other 4 stations located in the valley. So yeah, you can use this arithmetic mean method because it's like it has to represent the watershed correctly. Other than arithmetic mean method, this is the most favorite one, I guess, because it's usually used by a lot of people, a lot of students taking their thesis, bachelor thesis, using this method while calculating the average rainfall area. So this method, you have to understand it correctly because it will be useful in your future in your other assignment. For example, in the exercise, we will also talk about this method. So the this method takes into account the area represented by the station in question or area of influence to be used as a factor in calculating the average rainfall. For example, here we have different picture than before. Here we only have like, for example, here we have four stations in one watershed. As you can see, in one watershed, they divided it into different area. According to Thiessen, the area of influence of each station is determined by first connecting station with a line to form a triangular polygon. So for at first, the watershed is only maybe you can understand it better if I use the annotate. Okay. So the watershed area is this line right here, the outer line. Then at first step, we have to connect station with a line to form a triangular polygon. At first, we only have like this dot here, dot right here, the dot right here, and this dot right here. At first, we have to connect the station. Here we have four stations. We have to connect them. Between the dot, we have to connect using a line. Oh, okay, yeah. This line 1, 2, 3, 4, and don't forget to connect this also. And then after we connect the station with a line, we draw the axis of the triangular polygon. For example, here we can draw the axis of the triangular polygon by using the maybe different color. Here we have for this line we have the like the middle point of each line, right? This one we have here, this one we have here, this one we have here. And after we got the middle point of each line, we can draw the longer line here. Here we have here, Here we have here, meeting here. This one meeting here. One meeting here. This one meeting here. Yeah. So the intersection of this axis will form the area of influence of each station. Here we have the area of influence of station A in green area. And then we have the area of influence of station B in yellow area. And then here we have the area of influence of station D in blue area. Oh, that's correct. And then last one, we have the area of influence of sections station C in orange area. Yep. And the area of influence of each station divided by the watershed area. Here, watershed area is the total area, is known as the Thiessen coefficient of each station, which means the weighting factor, usually used as W in the next equation. So I hope it can be understood correctly. Yeah. So if you got the watershed map, and then there are stations of rainfall there, you can draw the Thiessen polygon correctly. Oops. Oh. Okay, let me clear the drawings. Yeah. So for example, because I draw it with only 4 stations, but here the equation is for 5 stations. So the Thiessen coefficient would be the weighting factor, the W. For each station has each weighting factor or Thiessen coefficient. Here we have the area of influence of station A divided by the total area. And for weighting factor of B is the area of influence of station B divided by the total area. And then we can calculate the average rainfall in the end by using the weighting factor W, multiply with the average rainfall from each station. And here you have to be aware that the total of the weighting factor should be equal to 1. So the WA plus B plus C plus D plus E have to be equal to 1. So the ratio is correct, the calculation ratio, because the area of influence, the total area of influence has to be equal to total area of the watershed. So the all of the area in the watershed is counted correctly. Yeah. For example, here we have like example of the picture with 5 watershed. Oh no, 5 stations. 1, 2, 3, 4, 5, and there are also border on each area on each station. For example, here we have 1, 2, 3, 4, 5, and then we got the W of the station A, station B, station C, D, and E, and then we can calculate for each month. For example, here in the November. In November, we have data from the station A the rainfall height of 121 millimeters. And then we got the weighting factor of station A of 0.16, and then we can multiply it with the rainfall from the station A, and then we got the WA multiplied with RA equal to 19.36, and we calculate for other station also, and then after we calculate for 5 stations, we can get the average rainfall with calculating with totaling the rainfall from each station. For example, here we calculated with totaling 19.56, with 29.12, with 18.96, 69, and 29.9, and then 11.43. Then we got this 108.5 rainfall average of month of November in this watershed. And same goes with other month also, with the same equation but different values, and then we got the average rainfall of the month of December in this watershed. And then move to other method. There is isohyet method. Here is rarely used because it has to be we have to draw the line first before we can use this method. The isohyet is a line that connected places that have the same rainfall height. For example, here we have station A, B, and C, and D in the picture. And then we have a line. In the picture, we can see that there is line 1, 2, 3, 4, and 5. At first, we didn't have this line. We only have this watershed with the point of rainfall station. How do we get this line? This line can be drawn if we know the rainfall height on this area. How can we know the rainfall height on this area? Yeah, we can determine it by knowing the data of the rainfall in these stations. But this method is most accurate, but it's quite difficult to calculate. In general, it is also used for annual rain because there are too many variations for daily rain. If we use the isohyet method for daily rain, I'm sure we cannot draw the line properly because there are too many variations for daily rain. So the isohyet will be fluctuate. So for this isohyet method, we can also calculate the average rainfall. We calculate the average rainfall by using this equation. Like for example, we got the I1 here, I1 and I1 plus 1. For example, here we got the I1 and I2. And after that, we have the data of the I1, I2 until I5. And to averaging this data, we have to calculate it by using this equation with x equal to A1 divided by total A. Here is the area. For example, for the x1 is the area cut by the isohyet line number 1 divided by the total area of this watershed. So it's similar to the weighting factor, but for the weighting factor, we got the line based on the polygon Thyssen, based on the Thyssen polygon. But here we got the line of isolated method based on the area which has the same rainfall rate. And it's quite more complicated than the polygon Thyssen, because here we got the for this area we have to calculate it not with the straight line. We have to calculate it based on this irregular area, so it's quite more difficult than the Thyssen method. And after that, we can calculate the average rainfall based on the rainfall on each isolated line. And the last one is the intersection line method. This is the simplification of the isolated method, because here we have the we got help from the intersection line, because if we only got the isolated, it is harder for us to calculate the area of this from each station. So here we have the intersection line method. So this one is the isolated method with intersection line. Here the green one is the intersection line, the red one is the isolated line. The amount of the rainfall at the intersection point is obtained from the interpolation of the two isolated data that flank it. For example, here we have isolated data number 1 and number 2. If the isolated line 1 is equal to 10, for example, 10 millimeters, and then for the isolated number 2 is equal to 20 millimeters, we can get the data of this rainfall point here, 3 rainfall point here, by using the distance between this rainfall point to the isolated line number 2 and isolated line number 1. So we can compare it. It is nearer to isolated line number 2. So the amount of the rainfall in this point will be similar to isolated point number 2. Maybe it's near to 20, but it's less than 20. So it maybe it will be like 18 or 19 millimeter, for example, like that. The mean rainfall of the watershed is calculated using the arithmetic mean method, using the rainfall data obtained at the intersection point. So here, for example, from this area, we got 3 intersection points. Here we have 3 intersection points. So we can calculate the average rainfall data for this area by averaging the rainfall points from these 3. So here, for example, is 18, and then here is 18. For this middle one is a little bit far from 20, so maybe it's 16 or 17. And then we can calculate the average by using the arithmetic mean method. So this one is simplification of the SOYAT method, but it's like a collaboration method between SOYAT and arithmetic mean method. And besides the average rainfall, we can also calculate the maximum of average daily rainfall. It has to be also understood correctly, because this maximum average daily rainfall, because of its complicated name, sometimes people mistaken this for the maximum of the daily rainfall, and then averaging the maximum of each day. But the steps can be calculated with the arithmetic mean method or the Thiessen method. And then after we got the average, we have to find the biggest from the average rainfall. So this one is the maximum average daily rainfall. Not averaging the maximum, but maximize the average. For example, here we have the data for daily rainfall data in year of 90. Year of 90, there are 5 stations, station A, B, C, D, E. And we have to calculate the average first, daily average from the same date, like from 1 January. From the 1st January, we have like daily average of this data here, for example. And then after we got the average of each day, we have to find which one is the biggest. So after that, we got the maximum average daily rainfall. So it's not like we look for the maximum from each rainfall, but we have to calculate the average first, and then we look for the maximum of the average. And in calculating the average rainfall, we can decide how many stations that we need based on the area of our watershed. Like here, for example, we have small area of watershed. It's only consists of 250 hectares. It is still considered small. It's actually quite like big as one village, I guess. And if the area has small topographic variation, which means the area is quite flat, not mountainous area, not area of some of the area of mountain, and then the other area is valley, no. So small topographic variation means the area is quite flat. So if the conditions like that, one station is enough. So you don't have to look for other station with the far away distance from your watershed area. But if your watershed area is less than 250 hectares and has small topographic variation, you can use rainfall data from only one station. So it can be said that this data from this station is representing the watershed correctly. And if you have a bigger area, for example, here until 50,000 hectares, you have to look for 2 until 3 stations with using arithmetic mean method, because it's quite big. So one station is not enough to represent all of the watershed. So you need more than 2 until 3 stations to calculating the average rainfall in your watershed. And for the watershed area of 50,000 until 120,000 hectares, you need more than 3 stations. And you can also use the arithmetic mean or Thiessen method. It depends on your topographic variation. And for the watershed area more than 120,000 hectares until 500,000 hectares, if the stations are evenly distributed and the rainfall is not affected by topographic conditions. You can use the arithmetic mean method, but if the stations are not evenly distributed, you can use season method. Basically, are similar similar with the watershed area of 50,000 hectares. And if you have a very big watershed areas, more than 500,000 hectares, you have to use the isohyet method or intersection line method. Besides the rainfall average, we also can classify rainfall from our previous meetings. We already know about heterograph. Heterograph is the shape of the graph. No, it's the graph between the time duration of the rain and the intensity of the rain. So here we have rainfall classification of 4 types. The first one is the uniform pattern, and then the second one is the advanced pattern. The third one is the intermediate pattern, and the last one is the delay pattern. This rainfall classification is based on the shape of the heterograph. Here for the uniform pattern, it means that the intensity of the rain is the same from the beginning until the end of the duration of the rainfall. But for the advanced pattern, the intensity of the rain is higher in the first, and then it's gradually decreasing until the rain stops. And the intermediate pattern is when the rain is gradually increasing until the peak duration, and then gradually decreasing with the same duration between the increasing and the decreasing time of rain. And for the delay pattern, the rainfall intensity is higher in the end, nearing the end of the duration of the rainfall. Because of the different classification of the rainfall, there is a relationship between rainfall intensity and the rainfall duration. So the magnitude of the intensity and the timing of the rain events have a big influence in the calculation of the design plot due to rainfall. As you know, a big value of the rainfall can influencing the plot discharge. So this relationship between rain intensity and rainfall duration is important if you want to calculate the design plot due to rainfall. Rain with high intensity usually occurs for a short period, while rain with low intensity usually occurs for a long time. Maybe you already know this fact by experiencing rainy season before. Like usually if the rain is heavy, like the rain is heavy, but the period of the rain is usually shorter than the rain which is not heavy. Like for example, if the rain is coming heavily, the time duration is shorter than the rain which is coming with low intensity. So the amount of the average rain intensity for the time with the hour can be expressed by this equation. So intensity equal to the rain height divided by the time or duration of the rain. So from here you can see that the the same rain intensity can come from different rain height with different time or duration. The rainfall intensity can be obtained using empirical formula. So there are 4 empirical formula that usually used. Here we have first one is the Talbot equation. So the name of the formula is based on the professor name that like found the formula. Here we have Talbot equation, Sherman equation, Ishiguro equation, and Mononoke equation. The last one is the most frequently used, the Mononoke equation. Yeah, actually all of the equation is frequently used, but the Mononoke equation is the most famous one, and you can you will meet this equation again later in the next semester. For example, if you take drainage class, you can use this equation more frequent. And first, we will talk about Talbot equation. So the uses of this equation actually depends on the rainfall duration for some. In the case of Talbot equation, it is used for rainfall duration between 5 minutes to 2 hours. So for the short period of rainfall, if you want to calculate the rain intensity, the average rain intensity, you can use this Talbot equation. The equation consists of A and B as a constant and T as the time of duration of rains. For the A and B, actually you have to calculate it using this equation. Like for A, you have to calculate it using I, T, and N, which means this I is equal to precipitation in T minutes. Like it's the rain intensity or it's the precipitation which has happened in the short period of time, because usually this is used for rainfall duration between 5 until 2 hours. So you will get the data of the rainfall in, for example, if you want to calculate the time duration of rain in 5 minutes, you got the data of the rainfall in first minute, second minute, third minute, 4 minute, and 5 minutes. And then after that, you have to calculate the constant first for the A and B, and then you can get the rainfall intensity for the rainfall duration in, for example, 5 minutes. Because of this equation is empirical equation, so it is normal to have this complicated equation because it is empirical, which means empirical equation is really based on the experiment that has done before by these professors. So it really depends on the condition at the experimental take place. So yeah, usually empirical equation is more complicated than the normal equation. There's also Sherman equation. It's quite different than the previous one because here we use logarithmic formula for the constanta. You got the rain intensity equals to m is the constanta divided by t is the duration of the rain, power with n, which is also constanta. Here we can use the Sherman equation if we have the rainfall duration for more than 2 hours. And the other one is the Ishiguro equation. It can be used in all of the rainfall duration. There's no constraint with that. And it has this kind of formula. There's no logarithmic, but there is a square root here, which we don't use before in previous equation. For this Ishiguro equation, rainfall intensity equal to C as constant divided by square root of T as in time duration of rain plus D as a constant. The last one is the Mononobe equation. It's the simplest one. It's used for calculating the rainfall intensity of every rainfall duration. This Mononobe equation doesn't need any calculation of complicated constant because it has its own constant, which is 2 per 3, like 0.67 usually. Yeah. So the constant is always 2 divided by 3 here. And then we have the rain intensity equal to R24 is the maximum rain height per atmospheric or in 1 day or in 24 hours. And then we have the duration of the rain here as T in hours. So you have to be careful here because the other equation, the time duration of rain is in minutes. Only the Mononobe equation is an hour. Here we got the example of using a Talbot equation. For example, here we have the data of rainfall in 2 hours. As you know, the Talbot equation can only be used until 2 hours duration. So here we got the equation of the Talbot. Rain intensity equals to A divided by T plus B. Here we have to calculate the A and B first. That's the complicated thing. Compared to Mononobe, we don't have to calculate the constant. That's why I use this Talbot as an example. So we have data of rainfall in 2 hours. Like here we have 5 minutes, 10 minutes until 120 minutes. And then we have the rainfall intensity in those particular time. Like in the first 5 minutes, the rainfall intensity is 150, and then it's decreasing until it stops. And to look for the A and B, we have to also calculate the I square here. And then we have to calculate the total of I square and the total of I, the square of total I, and then I square multiplied by T, and then I multiplied by T. That's why we have this complicated table here. First, we multiply I with T, and then we calculate the I square, and then we multiply I square with T. And after that, we can calculate the A and B, as here we have the total of I multiplied with T, 17140, and then multiply again with total of I squared, and then minus total of I squared multiplied with T, and then multiply with total of I. And yeah, using this equation, we got the number of A and B constant. And then we can use this equation I equal to A plus A per A divided by T plus B, as here we have A as 3,843 and B as 24, and then we got the equation for rainfall intensity. And after that, we can use the rainfall intensity here, the equation here, using the T of 2 hours, ST here, 2 hours, and then we got the 120 minutes plus 24. And then after that, we got the average rainfall intensity of this rainfall. So you cannot like simply averaging it by this data of intensity of each minute. So you have to do it with the empirical formulas. Besides the rain intensity calculation, you can also calculate the height of the rainfall. So for the intensity is the height of the rainfall divided by the time duration of the rain. But for the height of the rainfall is simply the height of the rainfall, like how big is the rain happen in that particular time. For the calculation of the height of the rain, yes, we still have time, I guess. There are 3 types of calculation based on the time duration of the rain. Like if the rain happens between 1 until 10 days, it's different with the calculation of the rain, which just happens only less than 1 day or even less than 1 hour. So we can check here. First, we can estimate the amount of the rainfall which happened in 1 until 10 days using this equation, namely Hesper's equation. So we can estimate, for example, here, example 1, the amount of rain for 4 days is 180 millimeters. This one is the maximum rainfall in 24 hours. So you have to estimate the amount of the rain for 4 days if the maximum rainfall in 24 hours is equal to 180 millimeters. So here you can use this Hesper's equation because it can be used for 1 until 10 days. And using this formula, 362 log t plus 6 minus 206, we can use t equal to 4 days here, and then we got the 100 r divided by r24 equal to 156%. And after that, we can estimating the amount of the rain for 4 days equal to this R24 times 156% or 1.56 equals to 280.8 millimeters. So that's the height of the rain that happens for 4 days if the rain data is 180 millimeters as maximum rainfall in 24 hours. It will be different if the equation used is the Hesper's equation will be different if it's used in the time duration of rain less than 1 day. For example, here we have a time duration of rainfall between 1 until 24 hours, so it will be less than 1 day. We can calculate the average of the rainfall using this equation. Calculation of the average rain to the hour t, here RT, and then calculation of the height of the rain at the hour t. So this one is the exact height of the rain at this hour, but for the previous one, it's the amount of the rain until this hour. So it will be different. For example, here, here we have to estimate the height of the rain in 4 hours from the data. For previous example, we use it for 4 days. Here we use example of rainfall in 4 hours. From the rainfall data with R24 equal to 240. This is the maximum rainfall data in 1 day. So if the rainfall only happened in 4 hours, how big is the height? We can calculate it using this equation here, this equation right here. And then we got this number of rainfall, height of the rain equal to 191 millimeters. This is the height of the rain in 4 hours. How about if we calculate the height of the rainfall distribution for 4 hours from example number 1? For example, here we have example 1. Here we have example 1, the rainfall from the rain data R24 equal to 180 millimeters. If we use it, for this, okay, it should be example 2 because we use it 240 here. It's not example 1. For example 2 here, we have R24 equal to 240. And from this equation, we got the rainfall distribution at first hour, second hour, third hour, and fourth hour. But here, from this example number 2, we only got the number of the height of the rain in 4 hours. But here we can calculate the distribution of the rainfall in 4 hours. From the first hour until the second, third, and fourth hour. As you can see, the rainfall is decreasing near the end because it only happens in 4 hours. So yeah, it will end it in 4 hours. And the calculation results can be presented in this table below. Here we have calculation of the distribution of the rain height based on this X and T calculation. And the last one, no, it's not the last one. This one is from 0 until 1 hour. So yeah, the previous one is 1 hour until 24 hours. So this one is when the rain happened for less than 1 hour. We can use this equation as to calculate the height of the rain that happened during that time. For example, calculate the amount of rain in 30 minutes from the daily rainfall data R24 equal to 140. So for 30 minutes, for this equation, we already have the constants table. So you don't have to calculate the A and B yourself. But if this time duration of the rain is not matched with your problem, like here we got the amount of rain in 30 minutes. But how if we got the amount of rain in 31 minutes? Yeah, you have to interpolate it yourself. So here we have the 30 minutes, constant A of 124, and constant B of 1272. And we can calculate it using this equation as A here and B here. And then we got the R24 equal to 140. And then we can calculate, so the amount of rain in 30 minutes from the daily rainfall data of 140 is just 52 millimeters. That's how you use this equation. So the data has to be obtained first. So you have to know the daily rainfall data first. And then after that, you can calculate the height of the rain at the specific duration. Yeah, so that's all for today. Should you have any question, maybe you can ask now.
I have a question.
Yeah.
Okay, my name is Angelina, and I a little bit curious why for calculation the height of the rain, we use the time duration is until 10 days, but no more 10 days. Ma'am, thank you.
Okay. Yeah, good question. It is actually related to the previous meetings. As you can see here, if you still remember from our previous meetings, there is periodic precipitation. Usually it's shown as the in Indonesia hujan 10 harian. So it calculated as 10 days rainfall. That's why here we use 10 days as maximum time to estimating the amount of the rain. Because if it's more than 10 days, you have to calculate it not using this Hesper's equation. You can calculate using this this equation. So you cannot calculate the rainfall for each specific of time. You have to divide it first by using the periodic precipitation. So it becomes more accurate. Because if it's more than 10 days, usually it's become too varied. So it can be harder to calculate. That's why we use here it is 10 days maximum.
Okay, ma'am, thank you.
Yeah, you're welcome. Other question? Tadi kayaknya ada yang raise hand ya. Pencet. Okay. I will upload it right after the class. So I haven't uploaded this presentation from our previous class because it's still connected to this one. And now we have finished this precipitation module. I can upload it full in my test classroom. And for our next meeting, there will be other new modules. It won't be more precipitation, but for this precipitation, there will be exercise. So you have to also understand it correctly, and you have to also prepare. It is related to this Thyssen method. So for this Thyssen method, usually the lecturer gives you this kind of watershed maps with some of stations. Usually it's 4 or 5 stations. And from that, you have to calculate the average rainfall in this area. So I think that's the most important thing from this module. For this precipitation module is the Thyssen method. Yes. Yeah, I hope you can understand it easily. If you have any question, you can also ask on the next meeting regarding this method or other topics. Okay, if there's no more questions, I think I can end today's meeting now. Thank you very much for your participation. tomorrow is not weekend yet, but yeah, have a nice afternoon and see you on Thursday. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Ma'am.